This example will show you how to perform the energy analysis of the ethylene plant in ASPEN+. To demonstrate how to use the activated energy analysis in ASPEN+, we need a converged flowsheet simulation of the ethylene plant. Let's return to the ASPEN+. So first, open the base case model of the ethylene plant from ASPEN+ examples folder by going to the Resource ribbon tab. Example. Then, select the Energy Analysis folder. Select the Ethylene Plant Base Case Model.bkp. Once you have successfully opened the file, go to File ribbon tab. Click Save As. Select ASPEN+ Backup to save the copy of this file in the other working directory to avoid the overwritten of the example files. Then, click Run the simulation again to make sure that it converges without error. The status shown here as Resource Available. So, we will start to perform the energy analysis. Click on the empty space on the Energy Analysis panel to launch the Energy Analysis configuration form. First, you need to set the approach temperature of the energy target calculation by selecting the process type. Because the refrigeration utilities are involved in the ethylene separation process, user needs to set the low temperature process to set the temperature approach at 3 degrees Celsius. If necessary, user can enter the carbon cost to calculate the carbon emission cost. By default, the cost is 0. The user can also define the scope to perform the energy analysis. User is capable of controlling which part of the flowsheets to analyze. User is able to scope out part of the processes if the flowsheet is modeled in hierarchical way. Even though it is not required, user is strongly recommended to define all available utilities to the plant in ASPEN+ flowsheet. User can utilize the Utility Assignment grid to define and assign the utilities to each unit operation block. In this file, all the utilities have been configured and assigned to the related blocks. Then, click Analyze Energy Savings button at the bottom of the grid. Or you can click On or Off button on the panel to activate energy analysis. Please wait for the program being calculated. Once the calculation has been completed, you will see the numerical values of the available energy savings shown in the dashboard panel, along with the green check mark at the top right corner. The potential utility savings found by the activated energy analysis are shown in two different forms. Here, it shows that the available energy saving is 12.19 megawatts, which is shown in the global enthalpy flow units for the flow sheet. This number corresponds to the 10% energy savings of the actual current utility usage. It is important to note that these results show the maximum possible savings opportunities as dictated by the thermodynamics, which calculated by the difference between actual utilities consumption on the flow sheet and the utilities target calculated by the pinch technology. These numbers do not represent any specific set of design changes. The user also have an option to select the basis of the showing results between flow and cost. I will keep the basis as the default of flow. The bar chart shows the breakdown on the total utilities, total heating, and total cooling in heat flow, as well as the carbon emissions in mass flow. The numbers are also listed in the grid below, which can be exported to Excel by clicking on See Report button. The Excel window of the report summary will be popped up. There are two sheets which show in the different bases of the results. To see more detail about the design changes suggested by ASPEN Energy Analyzer, you can go to the Design Changes tab. Or you can click the Find Design Changes button at the bottom of the Saving Summary sheet. We will discuss in detail about the design changes later on. In the Utilities tab, the user can view the detailed breakdown on the consumption and target for each utility. This form is organized in such a way that the hot utilities are listed at the top and the cold utilities are listed at the bottom of the grid. The actual and the target consumption is compared for each utility and the saving potential is calculated accordingly. So the saving potential is the result of the current minus by target. The energy cost saving in both absolute and the relative term are listed side by side with the energy saving potential. The user can also adjust the utility approach temperature, which is used to calculate the energy target. The Utilities Status column indicates if the utilities are sufficient in calculating heating and cooling targets. By definition of pinch technology, the total heating saving potential must be equal to the total cooling saving potential, which in this case, both of them are equal as 6.091. If the values are not identical, it typically caused by the insufficient utility or data extraction errors. To overcome the problem caused by insufficient utilities, it would be helpful to either adjust utilities inlet or outlet temperatures in the simulation or decrease the approach temperature in the configuration form to make them sufficient. The next form is the carbon emissions. Similarly, the carbon emissions tab lists the detailed breakdown of carbon emission and target, as well as the potential emission saving along with its cost savings for each utility. Note that the user needs to enter carbon costs in configuration form and activate emission calculation in utilities definition in ASPEN+. Otherwise, the carbon emission and cost would be zero. The Exchanger's form. This form displays the key information of the exchangers on the flow sheet. The users can hover the mouse over hot side fluid and cold side fluid to display the hot side process pin and cold side process pin's temperatures. In addition, the energy inefficiency in the current flow sheet is displayed in terms of the recovery duty for a heat exchanger. This information is valuable to help users to understand the design change solutions later on. Switching to Design Changes tab and click Find Design Changes to quickly generate up to 11 possible design changes to the existing flow sheet to achieve the energy saving opportunity. You might need to wait for a few minutes for the ASPEN energy analysis to complete the calculation. Before we go further into the detail of the design changes, there are 3 types of retrofit options that have been explored by the ASPEN Energy Analyzer. These include the Modify Exchangers, Add Exchangers, and Relocate Exchangers. The Modify Exchanger scenarios examines ways in which you can add area to existing exchangers to increase the heat recovery and, as a result, decrease utility consumption. This is a trade-off between saving energy and investing additional capital cost, and this scenario performs an optimization to minimize the total of energy cost and extra capital costs, subject to constraints of the maximum extra area and minimum temperature approach within the exchangers. This optimization option generates one solution only, as you can see here in the table below, under Add Exchanger Area. The second one is Add Exchanger. This option will add one new heat exchanger to the existing heat exchanger network at a time to reduce the energy consumption. This calculation designs on the optimum location for a new exchanger and the size of the new exchangers and new areas required in the flow sheet. The scenario generates up to 5 potential solutions, as you can select the number of cases you would like to evaluate here, but the maximum is 5 scenarios. And then the calculation results will be listed in the ascending order of the payback period. The last retrofit option is the Relocate Exchanger. The Relocate Exchanger scenario attempts to move an existing exchanger in the flow sheet to a new location to reduce energy consumption. This calculation designs which exchangers to move, the optimum location to move it to, and the new areas required on exchangers in the flow sheet. The scenario generates up to 5 potential solutions, which are listed in the ascending order of payback period as well. So, let's examine the results in detail. Tables in collapsible sections display the result of each type of retrofit option, where each design change of retrofit option type are listed in a separate row. For each change, the energy savings, payback period in years, new area, and capital costs are displayed along with the data describing the design change. The top grid shows the solution summary for modifying exchangers. In the ethylene demo file, 3,742.3 square meters of new area was added to the heat exchanger network to reduce energy by 2.5% with the payback period of 0.6048 years for this upgrade. The second grid here highlights the improvements found for adding a new exchanger to the process. Each row represents a possible location for the new heat exchanger. In ethylene demo file, the best option for heat exchanger addition solution will reduce energy by 9.9% with the payback period of 0.3905 years, resulting from the 5,064 square meter of new surface areas additions to the heat exchangers. The third grid highlights all improvement opportunities for relocating the existing CB3 exchanger in the process. In the ethylene demo, the relocation of heat exchanger CB3 reduces energy by 8% with a payback period of 0.243 years, resulting from 2,386 square meters of new area additions to the heat exchangers. It is worthwhile mentioning that the user is able to arrange the layout of the windows in the simulation so that the energy analysis form can be displayed side by side with the flowsheet. By this way, user is able to visualize the changes on the flowsheet easily. The solution should also try to eliminate the cross-pinch heat transfer in the flowsheet. However, the automatic solution process is much faster compared to manually coming up with a new idea on how to get rid of cross-pinch heat transfer in the flowsheet. Clicking the hyperlink on each grid in the form will take users to the details of energy analysis environment. For example, clicking on Add E100 hyperlink will take user to Node Scenario 2 in the energy analysis environment. We are now in the energy analysis environment with the Scenario 2 of adding heat exchangers E100 to the process. In the second table, in the Solution Details window, the specific heat exchanger addition solution desired by the user can be selected using the corresponding radio button. Since there are three options of adding new heat exchangers, select one of those options will affect the calculation result. However, we will focus on the solution with the smallest payback period, which is the first one. The first solution shows 5,064 square meters of the new area. Note that this area is the total area added to the entire heat exchanger network, instead of the area added to the new heat exchanger E100 only. In the third table, you will see the new heat exchanger E100 is added to the heat exchanger list and also highlighted as new. The initial solution from automatic optimization design is calculated without any constraints. For example, the maximum extra area and the minimum approach temperature are not constrained during the solution generation. The default values of the maximum new area allowed for each heat exchanger is set to be 10,000 square meters, as well as the default value of the minimum temperature approach also set to be at 2.4 degrees Celsius. For that reason, the new calculated total areas are very large in the initial solution. As you can see, the new area for CB3 is about 2,604 square meters, as well as the CB2 is 1,431 square meters. To refine the optimization solution, tighter constraints can be imposed on each heat exchanger by manually updating the maximum areas and the minimum approach temperatures as listed in the bold blue font. To illustrate this, enter 500 square meters in the maximum extra area for CB2 and CB3 process exchanger. And also put 0 square meters of the maximum extra area for the existing coolers of shield 2 and shield 4. Because shield 4 cooler require area more than the existing areas, as well as the shield 2 that the required area is almost the upper limit of the existing area. Click Update button to refresh the results. Upon completing this, the new area for both CB2 and CB3 are reduced to 500 square meters, which is the upper bound of the limits entered. Note, as a result of these constraints, the energy saving is reduced from 10% to 8.8%. Using this approach, the retrofit solution can be fine-tuned and the capital cost expenditure can be reduced. Keeping in mind that energy cost saving could also be diminished through more stringent constraints. An equation-oriented nonlinear optimization model enables users to quickly evaluate the trade-off between extra capital cost expenditure and the energy cost saving. You can also perform multiple retrofit operations in each scenario. For instance, adding a new exchanger after modifying exchangers in scenario 1. To do so, you need to go to the scenario 1, modify exchanger. Then click Add exchanger. The result of modifying heat exchanger area, followed by adding a new heat exchanger to the process, shows 9.9% energy reduction in the process, resulting in reaching the energy target. You can also compare the performance of each scenario by clicking Compare Scenarios button. Here, that is the comparison table of all scenarios that have been created, which showing the summary of hot and cold utilities, energy savings as megawatts and cost, as well as the new area required, extra capital cost, and the payback period for each scenario. This example is just the guideline for you to practice using energy analysis in ASPEN Plus to design a more sustainable chemical processes. You should do more practice to understand how these features work and how you can make most of the benefit from the process simulator tools such as ASPEN Plus.